Hello, my name is Frank Noé. I'm from FU Berlin, and I will speak today about variational methods and deep learning for high-dimensional dynamical systems. And we are very interested in developing machine learning methods for physical problems. Now, if you consider AI or machine learning methods in general, there are some famous examples that I'm sure you'll know. So, for example, there are all of these control problems around building robots that maneuver in complex environments or do tricks such as this one. There is reinforcement learning used, for example, in the AlphaGo system of Google DeepMind to learn to play Go. And when we develop machine learning methods, then we always have to think about two things. So what is the goal? What's the learning goal? What's the optimization problem? So for example, is there something like a loss function that we can minimize, and what is that? And what is the learning structure? So what is the structure that holds the parameters, and what does this induce about our problem solution? What does it mean for our problem solution to have a certain structure? And in physics applications, we often have a lot of physics background which tells us something about these two choices. So what is the optimization problem? In many cases in physics, we do not have supervised learning where we are just trying to match given labels by minimizing some error of the label prediction. We often have unsupervised learning problems. And in many cases, we have deep physical statements about what is the quantity that we really want to optimize in order to solve a certain problem, such as a variational principle, for example. And same with the learning structure. So in many cases, we have certain requirements on a machine learning method that makes predictions for physical systems. We want certain properties. We want maybe certain symmetry, certain conservation laws, certain invariances to hold. And that means we should probably build that into our learning structure because that makes learning easier and it can avoid catastrophically wrong or simply stupid predictions. Now I will focus on molecular physics here, and I will specifically focus on the sampling problem and the kinetics of molecular simulations. That is all atom molecular simulations where we model how, for example, proteins behave. These are two small proteins, really small, and the simulation system with them is about 100,000 atoms large. We are interested in how these proteins find and bind each other, how long it takes to do that, how long it takes to dissociate again, how that would change if we make little changes to the protein, such as mutations, etc. And we can do simulations for that. We have simulation models, such as energy functions. So these are that's a long story where they come from, and they can also be machine learned. But let's say we somehow have an energy function that tells for every state of the system, so for every positioning of atoms in space, how happy the system is, how energetically happy the system is, and that will translate into a probability distribution that we want to eventually sample in the long run. But we also want to sample how it gets from state 1 to state 2, so dynamical information. So we want both. Okay, so how do we do this? We can simply do all atom molecular dynamics simulation of this system, which is basically some sort of diffusion in this energy landscape. And there are very efficient programs for this. And these very efficient programs, if we run them on GPU, a state-of-the-art GPU for 1 week with this system, we get about 1 microsecond of simulation data. 1 microsecond of simulation data. If we do that 50 times, so for 1 GPU year, we get a single binding event for this system. And that is still doable if we don't do it in one trajectory, but we parallelize it. But the dissociation, that's the big problem, because it takes 1 hour of real time to dissociate this system, and that would be 1 million GPU years, and that is simply completely infeasible. So this is the sort of problem that we are facing here. That's a so-called sampling problem, and we want to know what methods can be used, what can we do in order to beat the sampling problem and still compute quantities such as probabilities to be in bound, non-bound, such as transition rates from bound to non-bound, etc., without having to simulate 1 million GPU years. First, I will talk about dynamical models of high-dimensional stochastic systems. And as an example, I will use Markov state models of molecular dynamics. So molecular dynamics, That's usually a very high-dimensional system where we simulate, for example, a protein and its solvent and a ligand which is binding to this protein and everything in all-atom resolution. So very high-dimensional system, and this is difficult to simulate because these systems have long-lived states, so states where the system stays in for a long time on average. And these long-lived states or metastable states can be thought of the basins in an energy landscape, so kind of minima in an energy landscape. And the transition between these metastable states is rare, so it's a rare event because it goes through less populated states such as barriers. And but there are also often many not so rare events that are traversed on the way. And the hope is with something like a simple dynamical model, such as a Markov state model, we can describe the transitioning between these substates. So we have to be able to identify what are the slow processes, the slow motions or rare events in such a system based on the simulation data. And so we have to be able to partition this high dimensional simulation trajectory into the relevant substates. And this is a difficult problem. And this problem does not only arise in molecular dynamics, but basically in every dynamical system. And we will come to that later. Problem. So instead of thinking of a trajectory as a time series, which stochastically jumps around in the state space and stays in certain states and transitions to other states, you can also think about the statistics of the system. And in that way, you think about an ensemble of simulation trajectories which evolve in time. And if you think about an ensemble of molecules, then at any time, these are following some certain probability distribution, and let's call this rho 0. And now we can think about this ensemble of changing this probability distribution towards its equilibrium distribution. And this is modeled by such a linear operator here, T of tau, the transfer operator. And what this operator does is basically just propagating the dynamics, and it models really all of the complications that are in the molecular dynamic simulation. So which integrator you're using, which thermostat, which force field, etc., etc. So this is a super complicated object, and we will not be able to characterize it explicitly, like write down an equation for it, but we can still analyze it well enough in order to derive algorithms that are useful. And an important approach here is to say we can do a spectral decomposition of this equation. So basically, under very mild conditions, this operator can be decomposed into eigenvalues and eigenfunctions which describe the dynamical change to this probability distribution. And so this expansion here has eigenvalues, and we can write them in this form for the slow transitions of the system, which is what we are most interested in here. Then we have some amplitudes, which depend on the starting distribution and the eigenfunctions, and then we have the eigenfunctions, which describe the mechanisms at certain timescales. Okay, let's see in an example what is happening here. So here we have a system with 4 wells. So there's an energy landscape with 4 wells. So that means we have a dynamics in this energy landscape with 4 metastable states in this minima. Okay. So now the spectrum, so the eigenvalues of this decomposition here will have 4 eigenvalues that are close to 1 because there are 4 metastable states. One of these eigenvalues will be equal to 1. This just corresponds to the fact that there is one equilibrium distribution, one unique equilibrium distribution in the system, and 3 eigenvalues will be close to 1 but smaller than 1, and they can be translated into timescales or rates via this form here. Yeah, so the whole thing is the eigenvalue, kappa is the rate. And that means small to 1 means there's a small rate here. So we have 3 slow relaxation processes with small relaxation rates. These are actually rates of the physical system that are really measurable in physical experiments if we have a suitable observable that can probe this process. For example, such as in fluorescence correlation spectroscopy, we can measure these. Okay, and the eigenfunctions here, they tell us something about the mechanism that the dynamics is undergoing at these different time scales or rates given by the eigenvalues. So in this example, the first eigenfunction is just the constant function. So this corresponds to the equilibrium distribution. That's not so interesting here. And the second one is such a step function, where it changes sign between this A and B and Z and D states. So it changes sign exactly at the barrier here, and that means the slowest transition, which has the smallest transition rate here, or relaxation rate, is the transition which jumps across this high barrier. So that means at that time scale, the system separates between a metastable state here and a metastable state here. And then at the next faster time scale, this eigenfunction here separates the left state into these two substates, A and B. And at the next higher rate, this blue eigenfunction separates this state into C and D substates, and so on and so forth. So now, if we want to model this dynamics, these slow dynamics, what's really important is to get a model for this transfer operator which gets the largest eigenvalues and corresponding eigenfunctions right. Yeah, and to see that, let's look at an even simpler system than this 4-well system, just a 2-well system. So we have two metastable states and we have one transition barrier between them. And let's say we do an MSM with two states. Now, if we choose the two clusters such that we don't exactly find the transition barrier between the two states, but we are a little off, then essentially we are approximating this eigenfunction here, the slowest process eigenfunction, which is the red one in this example, with a step function, because we have two clusters, so we can make one step between. Yeah, and this approximation is bad because we didn't find the separation place, so the transition state exactly. So we have a large error, and that means we will get the rates, the transition rates between the two states really wrong if we estimate such a Markov state model. Okay, if we get the separation between the two states right, so we place the boundary between the two clusters perfectly, we will get a pretty good MSM. But we still have a significant error. And we will do an even better job if we use more than two states. So instead of two states, we just use more states. We separate the transition process into finer steps, even though they are really just two metastable states in the system. But then we can approximate this eigenfunction with more than one step. And so we can make a smaller error and we'll get a better approximation of the transition rate. And as a result of these findings or these ideas, there was a proliferation of Markov state models with many, many states, thousands, 10,000, even 100,000 of states. Because the idea was, well, if we partition just fine enough, then we can avoid this bias which comes from a coarse approximation of the eigenfunction, and then we can still recover the correct dynamical information. But you already see probably that this has its limitations. So of course you have finite simulation data, so just estimating something with 10,000 of clusters or so has other problems. For example, it gives us large statistical errors and a large variance in these estimators. So we want to do a better job in approximating the dominant eigenfunctions and eigenvalues without having to do this, without having to make the model so large and complicated. So the question that arises is, can we somehow approximate the eigenvalues and the eigenfunctions in this expansion of the dynamical operator directly? Yeah, can we approximate them with some model, even though we do not know in advance what these eigenfunctions and eigenvalues are? And so in 2013, we developed this variational approach for Markov processes, originally called variational approach for conformation dynamics in these papers. And the idea is the following. We can indeed approximate these eigenfunctions in a general way because we can formulate a variational principle that we can optimize, that we can turn into an optimization algorithm. And the basis is this statement. So the first eigenfunctions of such a dynamical propagator are the solution to this maximization problem, where we basically compute the time autocorrelation function of functions that we vary. So these are some sort of ansatz functions or feature functions that we are trying to optimize. So we start with some function and we compute the time autocorrelation function. And that's something we can do from the simulation trajectory, so from the data, and we try to maximize them, subject to some constraints. Okay? And the maximum value of this sum is just the sum of the corresponding eigenvalues in the dynamical propagator. So this is a principled approach to approximate the eigenfunctions and the eigenvalues of the propagator, even though we do not have an explicit form of this propagator that we can actually compute. All right, and now if we do something particularly simple, when we say we want to learn these functions by doing a linear superposition of basis functions, then this becomes a linear algebra problem. This whole optimization problem becomes a linear algebra problem. And then it becomes something that is actually known since quite some time, since 1994 at least, and it's called TICA, time-lagged independent correlation analysis. And what we need to do in order to solve TICA is the following. We compute the time autocorrelation functions and the normal autocorrelation functions of all pairs of basis functions under the trajectory. So we get two matrices, a correlation matrix and a time-lagged correlation matrix. And then we solve this generalized eigenvalue problem with these two matrices. And then the eigenvectors of this eigenvalue problem, they approximate our eigenfunctions of the dynamical operator, and the eigenvalues approximate the eigenvalues of the dynamical operator. So under this assumption where we model the eigenfunctions as a linear sum of basis functions that we prescribe, this is the optimal solution. And this gives us often very nice dimension reductions. If we take the first few eigenvectors here and project the system into them, then we can get a low dimensional space, a low dimensional representation of the system dynamics in which we can nicely separate our slow processes. So simple example here, we have a dynamics which is jumping on a rare event basis between these two clusters, and whenever I am in one of the two clusters, I'm just outputting states by sampling from a Gaussian distribution, which looks like this, so it's stretched in the x direction and it's narrow in the y direction. And so if I would do, for example, principal component analysis on a system like this, then I just follow then I just find the direction of large variance, which is this direction. So projecting on the first principal component will not be able to separate the two long-lived states. But if I do TICA, then I nicely find this direction as the slowest direction, so as the most important direction. And if I project the system along there, I will find two nicely separated modes. And then I can find my two metastable states. And then, for example, I can do clustering in this state, in this space, and construct Markov state models with relatively few states that are still high quality. Okay, and so here is the connection between Markov state models for molecules and dynamical decomposition algorithms in dynamical systems and fluid dynamics that are established there. So in dynamical systems, we have things like dynamical mode decomposition from 2010, extended dynamical mode decomposition from 2014, and other algorithms that are similar. And these algorithms are actually extremely similar to TICA or this variational principle. And actually, the extended dynamic mode decomposition is exactly the same like this variational approach for Markov processes from 2013. In the last couple of years, this variational approach was generalized to Vamp. So Vamp is variational approach for Markov processes and is more general than the variational principle I've shown you before. The variational principle I've shown you before is based on approximating the eigenvalues and the eigenfunctions of the dynamical operator. And that's a good approach if the dynamical operator has real valued eigenvalues. Real valued eigenvalues in a physical system means the simulation is in thermodynamic equilibrium. So it's not driven, it's not out of equilibrium or in some sort of steady state or relaxing towards something that we haven't achieved yet. It's really in equilibrium. But often we don't have this, or we want to find long-lived states or slow transitions also in scenarios where we have some driving force in the system. And in other dynamical systems than molecular dynamics, we usually don't have this. So we usually don't have systems in equilibrium and with a real valued spectrum. Now, if in this case, it's not useful anymore to talk about the eigenvalues. It's more useful to talk about the singular values of the dynamical propagator. And this is because this is a decomposition which is always real valued. And we can always formulate a variational principle for the singular values, even if we cannot do it for the eigenvalues. And if the system is in equilibrium, then this more general approach, Vamp, will simply fall back to the original variational approach of conformation dynamics. So then it's the same thing. So this is truly more general. So we use this principle, the Vamp principle. And here is an example of what we can maximize to satisfy the Vamp principle. So here we need 3 correlation matrices, the current correlation matrix, the correlation matrix, which is just essentially evaluate the step tau later. So this is between the current and the current time step. This is between the next and the next time step. And then we have this dynamical correlation matrix between the current and the next time step. Now we compute this matrix product here and maximize, for example, the Frobenius norm. And this is one way to optimize the Vamp principle. Now, in both variational principles, what we basically have created now is a loss function or a score function. So we have an optimization principle. We have something that we can optimize, and then of course we cannot optimize this only for linear models or Markov state models or things like that, but we can really use deep learning now. And this is where deep learning comes in the analysis of these dynamical systems. So we can do now the following. We can use our simulation trajectory, take simulation steps t and t plus tau, so xt plus tau, put them at the input of 2 neural networks, and these could be identical neural networks, so they could be just clones, or they could be 2 different neural networks. And then each of these neural networks maps the input to an output. So this output is basically a representation, a generally lower dimensional representation of this high dimensional dynamical system. And now we optimize the neural network. So we optimize this encoding from the full system state to this latent representation by maximizing the Vamp score. Or if we are sure that we are in equilibrium, we can also directly use the variational approach for conformation dynamics score. Okay, so if we do this, we can get this low dimensional representation of the system, and with a simple linear transformation we can directly turn this into a Markov state model. Well, here we need an additional trick. We do not use an arbitrary output layer, but as an output layer we use a classification layer. So for example with a softmax function. And then that means every state at the input is associated with a membership probability in a long-lived state or a metastable state. And then if we have done that, if we have optimized this neural network, we can simply compute a Markov state model with this simple operation, and we're done. So let's look at the performance of these Vamp nets at simple dynamical systems, simple molecules such as alanine dipeptide. And alanine dipeptide has really the interesting transitions occur in this phi and psi torsion angles. So we often represent the system in such a phi psi plot, also called Ramachandran plot. And if we plot the density, the probability density of such a simulation trajectory, it more or less looks like this blue cloud here. And then these different states that you see here are the long-lived or metastable states of the system. So in this example, there are 6 states. This is these are periodic axes here. So this part and this part are connected. And now if we just apply Vamp nets, we train them on a simulation trajectory of this system, of simply the Cartesian coordinates of this system, we can find these 6 states very nicely. This is actually showing the result of such a Vamp net analysis. And this here are the 6 states illustrated in a Markov state model computed from this Vamp net. So the sizes of the bullets are the probabilities to be in the respective state, and the thicknesses of the arrows indicate the transition rate in this direction, so how probable it is in a given time step to move along this connection. And what's remarkable here is that the model learns that the torsion angles here are the important coordinates, and they give rise to a natural partition of the system, even though this information was not at the input. So we simply use the Cartesian coordinates as the input here. And on the right-hand side, you see what's often done as a statistical test of these Markov models. So here you just see the estimation of the relaxation timescales, or the inverse of these relaxation rates, which are related to the eigenvalues of the propagator. And here we see that the estimation of these quantities becomes approximately constant after a certain lag time. So if we choose a large enough lag time to analyze the system, and that's a sign that we are doing a good job of estimating the slow dynamics. And then here we are doing a so-called Chapman-Kolmogorov test. So that is basically comparing the predictions of our Markov state model for long times. And then we ask, if we go to the trajectory data, do we have corresponding transition statistics in these long time scales? So when we start in a certain state and we ask how much probability is left in that state after a certain time, is that equivalent to what the model predicts within statistical error? And this is a very nice agreement. And one of the more recent applications of this technique to a long timescale process involves adaptive sampling, basically a special form of reinforcement learning. And here the idea is the following. So if we have this process, this is the protein-protein association of Barnes-Barster, we can simulate these short simulation trajectories, but we cannot easily simulate the dissociation of the 2 proteins. So here you see a first step of association to some sort of intermediate. And if you simulate more, you will also see transitions into bound states, but you will not be able to escape these tightly bound states in simulation data that we can easily generate. But if we combine this simulation and analysis approach via Markov state models or Vamp nets with an iterative approach, such as some form of reinforcement learning, which decides at every given stage of the model what are the states which are most promising to start new simulation data in order to harvest statistics of events that we haven't seen, to see transitions that we haven't observed yet, and we go in loops, then we can get a complete model of Barnes-Barster association and dissociation with a total of 2 milliseconds data, despite the fact that the dissociation event from the tightly bound to the totally dissociated state takes about hours in real time. So it's order of magnitudes longer than the simulation data that was used. And here you see an illustration of what is happening in an association event. So the system basically associates first, and then it diffuses around, these two proteins diffuse around at each other's surface before they find the correct interaction point, or the docking of the binding site, and then basically the last connections are formed and the tight complex are formed that is so long-lived. So by combining all of these tricks, molecular dynamics, adaptive sampling, Markov state modeling, deep learning, etc., we can solve this system, this protein-protein association-dissociation problem with 2 milliseconds of simulation data. And in contrast to the 1 hour time it takes for a single dissociation event, this is actually something we can do. So, but despite the fact that we are like 10,000 times more efficient than direct MD, this is still obscenely expensive. And to see that, consider that for 2 milliseconds of all atom MD in this system, we needed about 20,000 GPU days, or in other words, 500 gigajoules. And to see how much that is, compare that to the energy it takes to burn a Saturn V rocket and move a 50-ton payload to lunar orbit, which is about 1500 gigajoules. So I think we're definitely burning too many rockets here, and probably we can do much more efficiently than this. And because that is so, we are trying very different approaches to sampling such many body systems. And here is an approach that is very different from pretty much anything that is done in all atom molecular dynamic simulations, or in simulation sciences in general. And here we really try to develop a deep learning method that approaches the sampling problem much more directly. And the idea is that since the system that we want to sample is defined via an energy function. So there's this energy function which models our molecular states and tells us in principle how probable these states are if we combine the energy function together with the definition of the thermodynamic ensemble, such as the canonical ensemble, for example. In that case, we have a Boltzmann distribution, and that is e to the minus energy divided by kT, for example. Okay, and so now the idea is, can we, since this is in principle all defined, so every state here, that every state X that we can probe has a known probability density. It's just difficult to actually explore the space and sample it. Can we do this more directly with machine learning? And the idea here is to use generative sampling or generative machine learning models for this problem. And generative learning, there are different types of generative learning. For example, a classical approach is restrictive Boltzmann machines. That's more like a sort of traditional sampling approach where you actually do learn an energy surface and then you do Monte Carlo updates in order to sample it. But there is also this class of directed generative models, such as generative adversarial networks, variational autoencoders, and normalizing flows. And all of these have in common that we want to learn a probability distribution and we want to learn to sample it. Okay, and the idea is to inject random variables from a simple distribution, such as an image where the pixel intensities are simply random noise, for example, sampled from a Gaussian distribution, each of them independently. And we inject that into a feed-forward neural network or another function that is trainable. And the aim is that at the output, we generate samples of the objects that we are interested in, such as samples of images of VIPs or celebrities, if that is something that we are interested in. And here is an example where a normalizing flow was actually used in order to do that. This is the GLOW model, a few years old now, so these things are much better now. But these are actually samples of images, of celebrity images generated by the flow. So this is really completely generated by the machine. And these people do not exist, but certainly they do look important. So the machine has clearly learned something about celebrities based on the images. Now we want to use this technology or to make it usable for sampling states of many body systems defined by a target energy. And here we use the techniques of normalizing flows. So in normalizing flows, we are learning an invertible neural network. So this is a bijection that is trainable. Okay, so for every point z, we can generate an x, and for every x, we can go back to z, and this is a unique mapping back and forth. Now we inject samples from a probability distribution that is easy to sample from, such as a multivariate Gaussian distribution, and we want to generate, for example, the Boltzmann distribution. We use normalizing flow, so we use an invertible neural network because then we can use the transformation of random variables rule, which allows us to compute the probability density of every x that we sample, given the probability density of the z that we did input, and the Jacobian determinant of the network. So if the neural network allows us to compute the first derivatives and the determinant of the first derivatives, this Jacobian determinant, effectively or efficiently, then we can use this approach. Okay, and a Boltzmann generator now is basically such a flow that we train to a target energy. And in contrast to machine learning, what machine learning normally does, we are not necessarily interested in learning the probability distribution from already given samples or data points, because we know the probability density up to a normalization constant. We just cannot sample it efficiently. So we actually want to make, we want to start with as few samples from X as possible, and we just want to make this distribution generated by the normalizing flow as similar as possible to the Boltzmann distribution. And then the second main difference to machine learning approaches to generative sampling is that we have a reweighting step here. So we generate a probability distribution, then we reweight this probability distribution to the target distribution, because we are interested in physics to sample really unbiased expectation values from a certain distribution. That is very important for physicists. Okay, how can we construct such an invertible neural network? There is a whole zoo of approaches available, but let me just give you one simple example, which is used quite a lot, and that is the so-called coupling layers. For example, nice or real NVP layers. And the idea is the following. We have these blocks here, so the blue and orange blocks are the blue and orange blocks here in the deep network. And each of these blocks has input and output variables, and we split the variables into two sets. Okay, and these two sets are transformed as follows. The first set is not transformed at all, so we just copy it to the output, so that's trivial to invert. And the second set of variables, we just do some affine transformations, such as multiplications or additions, as a function of the first set. Yeah, so for example, we do x2 multiplied with function s of x1, or we add function t of x1. And function s and function t are now neural networks, for example, dense trainable neural networks, and they are not invertible. And we don't need to invert them, because we can invert this multiplication or addition here in order to invert the xy direction. Yeah, and because x1 and y1 is equal, we can input y1 into S and t, and therefore we can invert this direction. And then we can stack these blocks deep. We can exchange y1, y2 after every such operation, so as to make sure to transform both channels. And we can stack these blocks deep and therefore get a deep invertible neural network that is trainable. How do we train a Boltzmann generator? Well, also here I just want to give you the main idea. The loss function that is minimized in order to train it, actually in order to make this practically work, consists of different parts. But the main idea is the following. So as I said, we want to go from a prior distribution that we can easily sample from to a target distribution, and we want to match that to the Boltzmann distribution. And we do that by, for example, minimizing the Kullback-Leibler divergence, also known as relative entropy, between the generated distribution and the Boltzmann distribution. And if you work that out, it turns out that the expression for such a Kullback-Leibler divergence is the following. And this is the expectation value over samples from the prior. Yeah, so here we sample z vectors from the multivariate Gaussian distribution. So this is easy to do. And then for each of these, we compute the following expression. This is the energy. This is our molecular energy that we know. So we have this energy function of the transformed variable. So we take the z variable, we push it through the flow, we generate a candidate for molecular configuration, and we compute its energy. So we basically minimize the energies of the generated samples. So if we would only do that, we would just collapse to a some sort of minimum energy value. That's not what we want. So we have a second contribution here, which is basically minus the log determinant of the flow transformation. And it turns out that thermodynamically this is an entropy. So we minimize an energy, but we maximize an entropy. So this entropy part prevents our probability distribution to collapse to a low energy point. And now we can do the same thing the other way around. So if we have samples available in X, so if we have already some MD samples, for example, in different states that are relevant for our problem, we can transform back through our flow to the C variables and then minimize the Kullback-Leibler divergence to the Gaussian distribution there. And this is equivalent to maximum likelihood training. Okay, and then finally, once we have trained the flow with a Boltzmann generator, we can turn the flow into a Boltzmann generator by using the flow to generate samples and then reweight them or resample them using Markov chain Monte Carlo, for example, in order to generate samples from our target distribution, the Boltzmann distribution. So let's see this in action. So here's first an example from a two-dimensional space. So we have a double well potential here, two minima with a high barrier in between. So it takes a long time to transition between these minima. And we start with points on the left and on the right, but without having seen any transitions between them. In this system, we should have many more samples on the left than right in equilibrium because this minimum is deeper, but we start with an equal number of samples. So basically, we're starting from the wrong starting distribution. Then we train this Boltzmann generator, so we transform this distribution into something that looks Gaussian in latent space, sample from it there, push forward to X, reweight, and then we can actually recover the true free energy along the X1 coordinate. So the free energy, that's just minus the logarithm of the marginal distribution in X1. Okay. Another interesting point, what we can do is we can take 2 points here. So for example, a blue and the red point, and then do a linear interpolation in Z. And then push every point along this linear interpolation forward to X. And then of course that is nonlinear because that's nonlinear transformation, and it turns out those are nonlinear pathways. And they can be quite good approximations to reaction pathways, to pathways that go through high probability density. So this is the situation when we already have data from the different metastable states that are of interest to us. But in many cases, we also want to explore. So we want to start maybe from one point and then find the other metastable states that are relevant. So the Boltzmann generator is basically a transformation method that allows efficient and fast sampling of states that we already know. So it's not really an exploration method, but it can be coupled with exploration methods. And there is a ton of exploration methods around in molecular dynamics, such as metadynamics, replica exchange, or simply high temperature dynamics, some bias dynamics, etc., etc. And here we do something very simple just to illustrate how this can work. So we start with one point. We learn a Boltzmann generator. So initially this will just generate samples close to this point because it doesn't know about this other state. But then what we do is we do Metropolis Monte Carlo in latent space. So we do very simple Monte Carlo steps in this latent space where we simply sample from a Gaussian distribution around our current point with a standard deviation of 1. And then we accept or reject with a metropolis step in X space. And because we can always go back and forth between C and X, we can always do that. We can always compute the acceptance probabilities. Then we may have found something new, we retrain, and we sample again. We go in loops. And in this system, you can easily see that you sample both metastable states. This way you soon find a second minimum, and then eventually you can converge to the equilibrium distribution this way. And in more complicated systems, you might need more clever exploration methods, such as I said, metadynamics, replica exchange, and so on. The strength here is you can now combine all of these things with latent space dynamics. Yeah, because the Boltzmann generator basically repackages probability density in latent space so that we have a compact representation of all the high probability states there. All of the metastable states are close together in this space. In this space. We can reformulate those methods there, and that may be more efficient than directly formulating them in X, where we have not such a nice structure. Here is a more interesting example. So this is a box with repulsive walls filled with repulsive particles with a 1 over r to the power of 12 potential. So these are very repulsive. You can't get them close to one another. And then we have two particles here that are special. This is sort of a dimer that can be close together or extended. And in both states, it's quite happy, but the transition state is a high energy barrier. So it's a rare event to open and close this dimer. And it's not easy to find moves, Monte Carlo moves, to do this because it's a dense system. So in this state, I couldn't simply open the dimer because I would run into solvent particles. Here, I couldn't close the dimer because there are solvent particles in between. But starting from these two systems, training the Boltzmann generator, we can efficiently sample the system and also find transition states. And the interesting thing here is we can also do that directly for multiple temperatures. So we can train with multiple temperatures to the target energy. So we basically train to a family of Boltzmann distributions at different temperatures. And then we can directly generate at these different temperatures. And the way we do this is by scaling the latent space, so the z variable. So we simply train such that increasing the variance in the Gaussians at the input is proportional to the temperature change. And for some flow architectures, this is actually an exact mapping. For the ones that we have used here, it's not exact, it's approximate, and therefore we need to find this temperature steering by training it. And the green lines that you see here were computed with umbrella sampling. So these are free energy profiles along the dimer distance at different relative temperatures. So the standard temperature, half that temperature, and double that temperature. And as you see, the Boltzmann generator samples correspond to the umbrella sampling simulations. How far can we push this approach? So here is an illustration. Then we can also hope to sample structures of peptides or small proteins. And so this is an illustration of a structure of BPTI, bovine pancreatic trypsin inhibitor, a small protein with about 1,000 atoms. And here is the all atom representation. And this is actually a sample, a one-shot sample from a Boltzmann generator. Yeah, so this was really generated by taking a sample from a 3,000 dimensional Gaussian, mapping it through a feed-forward neural network, and getting this out in one shot. And you can train Boltzmann generators to sample diverse structures, such as you see here. And here you see that the chemical properties of these samples are decent. So you have reasonable distributions in bond distances and bond angles, etc. And so this shows that with a sufficient number of tricks that we used here in order to encode the variable transformation between these x variables and the latent space variables, we can actually really hope to sample polymer structures, peptide structures, maybe small proteins. Of course, there are limitations here, and that's very important to understand. So here, basically, the big advantage is that we don't need to do these tiny little MD steps to move almost nowhere in an affordable computational time, but we can do these IID samples. So we can directly sample from the Boltzmann distribution or from something that's similar to the Boltzmann distribution. So that's wonderful. But the disadvantage, of course, is that we will never train the Boltzmann generator to sample exactly from the Boltzmann distribution. So we will always have a little bit different output distribution, and therefore we need to reweight. So the second step is extremely important. But the larger the system is, the more differences we will have between these two distributions, or the harder it will be to make them match. And therefore, the acceptance rate of this reweighting step will go down. So there's a balance here between doing all atom MD and just doing 1 femtosecond at a time, which is very inefficient, and it's still inefficient if we use enhanced sampling methods and Markov state models and all of these tricks. And on the other hand, trying to sample the whole system in one shot and reweighting it, which can be very inefficient if we have very large systems, because we eventually we don't accept samples anymore, right? So somewhere in between there is a sweet spot. And the idea is to use these approaches to exploit that sweet spot. And if you have a very large system, maybe break that down into subsystems, learn essentially clever Monte Carlo moves by applying Boltzmann generators to these subsystems, and then updating the entire system in such a Gibbs sampling sort of approach. Here are a few examples of other researchers that use these ideas, such as Boltzmann generators, in order to sample states for different systems, such as spin models of magnetic matter. This is, for example, done by Kim Nicoli, by Klaus-Robert Müller at TU Berlin, and many others. And then here is an example of lattice quantum chromodynamics. So those are relativistic models of the nuclear dynamics, and they give rise to very expensive and very complicated sampling problems in a lattice in 4-dimensional space-time. And for example, Fiala Shanahan is working on that together with Kyle Granma and Danilo Retzende and many others. And so this is becoming a very important topic in different branches of physics, where a target distribution is defined by some sort of energy or some sort of path functional that we want to sample against. So with this, I'm finished with my talk. I would like to thank all of my co-workers. So I'm very blessed with great students and great postdocs, and wonderful collaborators. And I also would like to acknowledge the organizations that have funded this work, mainly the European Research Commission, the Einstein Foundation, and Deutsche Forschungsgemeinschaft, the German Research Foundation. With that, thank you for your attention.